Alright, so let's take a look at some additional applications of finding maximums and minimums. Let's suppose the cost of manufacturing X obsidian gargoyles each day is given by this cost function. And also each gargoyle is sold for $100. How many gargoyles need to be produced to minimize the cost? Now, we probably had other ways of doing this in algebra, but if we want to use calculus, first of all, if we want to figure out when something maximizes or minimizes, we're going to use the derivative. And since we are minimizing the cost, we're going to take the derivative of the cost function. So the derivative of the cost function is the derivative of 500 minus 6x plus 0.2 x squared. This is going to be 0 minus 6 plus 0.4 x. And we found that the max and mins are going to occur at places where the derivative is 0 or undefined. So to start, I'm going to let the derivative equal 0. And we see that we can solve for x. We'll get 6 divided by 0.4, so 15. So we'll get x equals 15. Now x is the number of gargoyles per day, so this is 15 gargoyles. Now if you look at this function, there's no place where the derivative's undefined, so this is the only critical number. A critical number is where the derivative equals 0 or is undefined. Now maybe this is our answer. How many gargoyles should be produced to minimize the cost? Maybe the answer is 15, but we do need to check, because this could also be a maximum. Or this could be just another interesting point like an inflection point. So just because the derivative 0 does not guarantee this is the exact kind of point we're looking for. So let's do a quick check. Now, what we're interested in figuring out is the graph increasing or decreasing, or is it decreasing and increasing? What's happening? But we can use the derivative to figure that out. So I'm going to test this side of 15. And I'm going to test the x value of 0, because 0 is before 15, but I'm going to put it in the derivative, and we get negative 6. If the derivative is negative, that means the slopes of the tangent line of the original function are negative, which means the slope of the graph is doing this. It's going downwards. So if the derivative is negative for this whole region, then the original function is decreasing for that whole region. And we could test this side. I'll use 20 for x. And this goes in the derivative, so negative 6 plus 0.4 times 20 is positive 2. And if the derivatives are positive for this whole region, the slopes of the tangent lines look like this, which can only occur if the original function is increasing. So we have a minimum here at 15. So x equals 15 gargoyles produces a minimum cost. And it's worth mentioning that this minimum cost will be an absolute minimum. Now the reason for that, this technique here generally only finds relative max and mins. But if you look, there's only one critical number here. There's only one place where there's a max or a min potential. So there's not a whole lot going on with this graph. It's decreasing and then it's increasing, which means this relative minimum is pretty much going to have to be an absolute minimum. If there were a lot more things going on, if there were a lot more increases and decreases, we would have to look at the graph to be able to be sure if it's an absolute minimum or not. But x equals 15 is the only critical number on our interval. And like I said, critical number is just really the numbers you're getting for the zeros and the undefined. So it's the only one on our that we're testing. All right, so we're simply using calculus to find the relative max and mins in order to figure out when this cost should be minimized. All right, so let's take a look at this example. How many gargoyles should be produced to maximize the profit? Now here, we want to maximize profit, but we do not have a profit function given to us. So if I want to use calculus, I need to find a profit function. And the first thing to note is you may remember that profit is equal to revenue minus cost. Revenue is how much money you bring in, cost is how much money you spend, profit is what's left. But you may also remember that revenue is equal to the price of each item times the number of each item sold. So we're selling each gargoyle for $100. So if we sell 5 of them, our revenue will be $500. So the price we know is 100, and the number sold, well, X is the number of obsidian gargoyles that we make. So let's assume that however many we make is however many we sell. And so that would make the number sold X. So we have a revenue function, which means our profit would be 100x, because that's the revenue, minus the cost, which is already given to us. So minus 500 minus 6x plus 0.2 x squared. And if we simplify this, we'll have to distribute this negative. The 100x and this negative 6x will become a positive 6x. So we'll get 106x minus 500 when we distribute this negative. And we'll end up with minus 0.2 x squared. So now we have a profit function. And if we want to figure out what x value maximizes it, then using calculus, we're going to start with the derivative. And the derivative of profit will be 106, because that's the derivative of 106x. The derivative of 500 will be 0, and the derivative of 0.2x squared will be negative 0.4x. And remember, step 2, look for where the derivative is 0 and undefined. So if we set the derivative equal to 0, we can solve for x. And so this is going to be 106 divided by 0.4, and that'll give us 265. And because x is the number of gargoyles, this will be 265 gargoyles. So all that's left is to know, is this a max or a min or neither? So we're going to do a check. So I want to know if the function's increasing or decreasing. So I'll test a number before 265. And 0 is kind of an easy one to plug in. And if you plug in 0 for x into the derivative, we get 106, which means the profit is going up. And let's say we test 300 into the derivative. So this will be 106 minus 0.4 times 300, and we get negative 14. So if the derivative is negative, the profit is decreasing, which means we have a maximum here. And that's what we wanted to find. So x equals 265 gargoyles. Produces a maximum profit. And note, this is also an absolute maximum profit for the same reason that we had above. Since 265 is the only critical number that we were testing. So let's say we want to build 6 chain link fences. Now the total area of all the cages needs to be 12,500 square feet. The exterior walls of the cage, so all these exterior walls cost $30 per foot, but these interior walls only cost $20 per foot. What dimensions are needed to minimize the cost of building this cage? Now, we're trying to minimize cost. So calculus is pretty useful here. But we need a cost function because the first thing we would normally do is try to find the derivative. So we need a function for cost. And we're going to have to build one. Alright, so what is going to be the cost of this thing? Well, let's say that this side is a length x, and this side is a length y. So all of these lengths here are x feet long, and all of these lengths here are y feet long. This length right here costs $30 per foot. So this will be 30x. And this cost for this length of the fence right here will also be 30x. But this is an interior cost, and it's only $20 per foot, and we have x feet. So far, these 3 lengths cost us 30x, 30x, and 20x. This length is a length of y, and it's an exterior length, so it'll cost us 30y. This one way over here will also cost us 30y. But now we have 2 interior lengths. So 20y and another 20y. So overall, our cost is set to be 80x, 30, 30, and 20. And then we have 30, 30, 20, and 20, so this is going to be 100y. Now, even though this is a cost function, it has 2 variables in it, x and y. And we've never dealt with a derivative that had multiple variables like this. So we have a little bit more work to do. And one thing that we can use is the fact that the total area is going to be 12,500 square feet. So area is equal to 12,500 square feet. This is a constraint for this problem. But we know that area of this whole thing is going to be length times width. So x times y equals 12,500. And so if we solve for one of these variables, we can plug it back into our original cost to reduce the number of variables we have. This is a system of equations. We have 2 equations with 2 variables. We can solve for one and plug it into the other. Doesn't matter which we solve for. I'm going to go ahead and solve for y. Which means that cost is 80x plus 100 times, instead of times y, it's going to be times 12,500 divided by x. So this will be 80x plus this 1,250,000 divided by x. And so now we have our cost function with one variable. All right, so this first part here, this is just some algebra work to get a cost formula. Our goal is still to minimize the cost. And if we want to do that, the first thing we're going to do is find the derivative. So the derivative of cost is going to be the derivative of 80x. And looking at this, this will be a quotient rule unless I rewrite it. So I'm just going to go ahead and rewrite it before I take the derivative as this 1,250,000 x to the negative 1. So I'm going to bring the x up into the numerator. So the derivative of 80x is 80. The derivative of 1,250,000 x to the negative 1 is negative. That number, x to the negative second. All right, so now that we have the derivative, if we want to minimize the cost, we want to look to see where the derivative is going to be 0 and where it's going to be undefined. So to start with, I'm going to set the derivative equal to 0. And if you want to solve an equation like this, probably a good strategy is to get rid of these negative exponents. So I'm going to write this as 80 minus this number divided by x squared. And I can multiply through to get rid of all the fractions. So we can multiply through by the LCD. And this will give us 0 equals 80x squared. Here the x squareds will cancel, so this will be minus 1,250,000. All right, and we can move this over. We can divide our 1,250,000 divided by 80, and we get 15,625. equal to x squared. And if we take the square root of both sides, we'll get 125. But square root will give us a plus and a minus 125. All right, so we've got our x values. However, right here we have an x in the denominator, so we should note x equals 0 is an undefined point. So we actually have three potential numbers to test. Negative 125 for x, a positive 125 for x, and 0 for x. Now remember what x is. X is this length. So it is the number of feet representing the width of our cage. Now we need to test this. And we've got three numbers here. Negative 125, 0, and 125. But you might be thinking, wait, negative 125 feet really doesn't make sense for this problem. Even 0 doesn't make a whole lot of sense, because it's the width of our cage. So that's true. In context of the problem, we don't care about this part of the graph, only this part. So there's really only one potential answer to this. Well, let's test it out. We need to test the cost, and I can't test 0 because that'll be undefined. So I'm going to test 1 into the derivative. And that will give us 80 minus 125, 0, 0, 0, 0 divided by 1 squared. So we're going to get a big negative number. So this is a negative number, which means the cost is decreasing. And I'm going to test 200 on the other side. So 80 minus 125, 0, 0, 0, 0 divided by 200 squared gives us a positive number. So the cost is increasing. So this will be a minimum. And it's going to be an absolute minimum, because this is the only critical number that's valid for this problem. All right. So x equals 125 feet. And it did say what dimensions. So that's the x. I probably need the y, but I can use this function right here. So 125 over, or 12,500 over 125 is 100. So y would have to be 100 feet. We'll minimize the cost. So for a problem like this, we had to first set up the cost function and then use calculus to answer the minimum. All right, so Here we have an example where we have an open box with a rectangular base, and it's going to be constructed from this piece of cardboard. Now the cardboard is 16 inches wide and 21 inches long. So here we have our 21 inches and 16 inches. And in order to create this box, we're going to cut a small square from all four corners and then fold them up and tape them together in order to create our box shape. Alright, now our goal is to find the largest possible volume that can be constructed. The largest volume. And the one control that we have here is how large of square we're cutting out of this rectangle. We weren't told what size that was, but we know it's a square, so all the sides will be the same. So we'll just call it, say, X. So X inches long. And if you can kind of visualize it here, if you fold this up, the X is going to be the height of your box. Alright, so like before, if we want to find a maximum volume, then we need a formula for volume so that we have something to take the derivative of. Now volume is length times width times height when we're talking about these kind of box shapes here. And we already know the height's going to be X because that's going to be determined by what cut we make into the cardboard. But what about the length of it? Well, if you've cut these rectangles out, then we're going to have 21 minus 2x inches for the base of our rectangle. And for the width, we'll have 16 minus 2x. So this volume will be 21 minus 2x times 16 minus 2x times x. And there, we have a volume formula. It only has one variable, so we don't have to do any of the substitution that we're used to doing. And if you FOIL all of this out, you'll end up getting 336x minus 74x squared plus 4x cubed. Alright, so we've got our volume, and our goal is to find the largest volume. And if we're going to use calculus, we need the derivative. Now the derivative of volume is going to be 336. 74 times 2 is 148x. And then 4 times 3 will give us 12x squared. So here is the derivative of this function. And if we want to find the potential maximums, we look for where the derivative equals 0, or where it's undefined. Now if you look at this function, there's no place where it's going to be undefined, but we can find where it's equal to 0. And it's a quadratic, so you're either going to want to use factoring or the quadratic formula. Very briefly, if you use the quadratic formula, you'll have 148 plus or minus. It'll be the square root of 148 squared minus 4 times a times c, so 5,776, and that'll be all divided by 2 times a, which is 24. And if you check this out, you should get 9.33 or 3, depending on whether you use the plus or minus. Now, since this is what x is, this is going to be the number of inches that we cut out of the corners of this piece of cardboard. Alright, but we should always check this because we've got 2 possible answers. It's worth figuring out what's going on. So we've got 3 and about 9.33. And let's test 0 into the derivative. And if you do that, we get 336, which is a positive number, which means the volume is increasing. So it looks like 3 might be the cutout that gives us a maximum. We need to test something in between 3 and 6. I'll test 5. So 336 minus 74 times, 336 times 5. Oh, we've got to test it in the derivative. So 336 minus 148 times 5 plus 12 times 5 squared. Let's make sure we put it in the right formula. We're testing the derivative. We get a negative number, negative 104, which means the graph is going downwards because all the slopes are negative. And I'll test 10 into the derivative at the end here. 336 minus 148 times 10 plus 12 times 100. And we get 56. So the function's going up. So we have a relative max here when we cut 3 inches out of the cardboard, and a relative minimum when we cut about 9.33 inches. But we have to be really careful here. So when x equals 3 inches, we get a relative max volume, but not necessarily an absolute maximum, because look what happens to the original volume function. The volume goes up until it peaks right here, and then it heads down until it reaches a valley right here at 9.33, but then it starts going up again. So the volume's getting bigger and bigger and bigger as you keep going with larger and larger cuts for x. I have no idea if the volume will eventually beat the maximum here somewhere way off here. It just goes up forever. So this is way too complicated a function for us to simply say this has to be the biggest possible volume. But you may have noticed that if you take another look at this cardboard, there's only so much cardboard you can cut. The width here is 16 inches, so if you cut more than 8 inches for X, you won't have a side. So, in fact, let's just take a look right here. If we expect 16 minus 2x to at least be bigger than 0, so you have a positive width, then the x has to be less than 8. So whatever makes 16 minus 2x positive means the x cannot be bigger than 8. So this really can't happen or you won't have a box. Now this means, since x has to be less than 8, this means we only have one critical number. So only one number is actually getting tested. So this relative maximum actually is an absolute maximum. So x equals 3 inches is an absolute max. In context to the problem, because the problem doesn't make sense if you let the x's get bigger than 8. So if you're not sure if you've got a relative max or an absolute max, you might have to go to the picture or the graph of the formula, but if you take a look at the problem, often you can exclude the thing that's causing trouble. All right. Now the question asked for what was the largest volume, which means we can say the largest volume is whatever we get when we put 3 in for x. And here the 3 is going to go into the original volume formula, not the derivative. The derivative tells you increase or decrease. The volume formula tells us the actual volume. So 336 times 3 minus 74 times 9 plus 4 times 27, which is 3 cubed. So 450 cubic inches will be our maximum volume. So again, if we take a look, we had to start by creating a volume function, then go through our derivative process, excluding anything that doesn't fit the problem, and then answering the question. All right, let's take a look at one more example. Suppose we have a road represented by this line right here, 6 minus 0.5x. And we have our campsite, which is located at the point 3, 1. So we're looking down on this like a map. At what point along this road should we stop so that we have the shortest walk to the campsite? So we're looking to minimize distance. Now, if we want to do this with calculus, then we need a distance formula. So let's first start by drawing a picture of the distance on the map that we're planning to walk. We want to go from the road to our campsite, but we don't know exactly where on the road we're going to stop. So let's just put in a made-up point. I'll call it x comma y, because we don't know what the x and the y are for that point on the road. And the distance we travel to the campsite will be this dotted line right here. So I'll label it capital D. So we need a formula for the distance. Well, in order to create this formula, let's use a right triangle. So we already know that the campsite is located at the point over 3 up 1. And the point on the road we said was x, which means this distance right here is actually x minus 3. Because from the origin all the way out to wherever the point on the road is, that's a distance of x, minus this distance of 3 getting to the campsite side from the origin, leaves us with x minus 3 left over. And from the x-axis all the way up to this point, that's a distance of y. But if we go up just 1, that's the height of the campsite. So the height here is y minus 1. And by Pythagorean's theorem, this side squared plus this side squared equals this side squared. So d squared would equal x minus 3 squared plus y minus 1 squared. So we want a formula for the distance. So if we take the square root, we get that the distance is the square root of x minus 3 squared plus y minus 1 squared. And one problem that we have is we've got two variables in the distance formula. We've got x and y. And we haven't taken a derivative with multiple variables in the formula before. However, the y we're dealing with is talking about a point on the road. And this is the equation of that road, so it's the equation that links x's and y's together. So the y variable is actually equal to 6 minus 0.5x. So we can rewrite this as the square root of x minus 3 squared plus, if we put 6 minus 0.5x in for y and subtract 1, we get 5 minus 0.5x. And it's not necessary, but I'm going to go ahead and FOIL all of this out, multiply it all out, and combine it together. And if you do that, you should get 1.25 x squared minus 11x plus 34. So it might take a little work off to the side, but this should be what you get if you use the advanced distributive property and then combine everything together. Now that we have a derivative, or now that we have a formula for the distance, in order to find the minimum distance, we can use calculus, which means step number 1 is to find the derivative. So the derivative, or d prime, is going to be the derivative of 1.25 x squared minus 11x plus 34 raised to the 1/2 power, because that's equivalent to a square root. And if it helps, feel free to use a substituting u. This is a composition of functions. So I'm going to let u be what's in the parentheses, 1.25 x squared minus 11x plus 34. So this will be 1/2 u to the negative 1/2 times the derivative of u by the chain rule. The derivative of u, I'll write it as u prime. So I need to know what u prime is. And the derivative of this is luckily pretty easy to do. This will be 2.5x minus 11 plus 0. So this will be 1/2 1.25 x squared minus 11x plus 34 to the negative 1/2 times 2.5x minus 11. Step 2, we set the derivative equal to 0. And if you want to solve this, let's rewrite it without the negative exponents. So 1/2 means 2 is in the denominator. This thing to the negative 1/2 means 1.25 x squared minus 11x plus 34 now to the 1/2 power is in the denominator, because that's what that negative exponent tells me. And then this will stay in the numerator. So 2.5x minus 11, all of that equals 0. And if you want to solve this for 0, remember the denominator's not going to make something equal to 0, so it's really just the numerator that we have to worry about. So 0 is going to equal 2.5x minus 11. And this will be 11 divided by 2.5, so 4.4. is what we'll get for x. All right. So the next thing we should do is check for any undefined points. So this thing is undefined when 1.25x squared minus 11x plus 34 is equal to 0. And you could pretty quickly catch that this is not going to be undefined. If you use the quadratic equation, you'll get 11 plus or minus what goes under the square root is going to be b squared, so it's going to be 11 squared minus 4 times a, which is 1.25, times c, which is 34, and you're going to get negative 49, all over 2 times a, which is 2.5. So there's no undefined points. So this is our only critical number that we have to worry about. All right, so the numerator gave me the zeros, the denominator would give me the undefined, but we didn't find any. And so now let's test 4.4 and see if this really does give us a minimum distance. All right. So if we test into the derivative, we could test, say, 0 should work. And we'll put that into the derivative. So 1/2 times, this will be 0, 0, and 34 raised to the negative 0.5. And then 2.5 times 0 will be 0, so times negative 11. And this gives us a negative number. So this is a negative number, which means the original distance function is decreasing. And let's test 10. So this will be 1/2 times 1.25 times 100 minus 11 times 10 plus 34 raised to the negative 0.5 times 2.5 times 10 minus 11, and we get the number 1, which means the original distance function is increasing. So this is a minimum. So the point that we're interested in is when x equals 4.4. And to get the y value, we can plug 4.4 into this function. 6 minus 0.5 times 4.4 gives us 3.8. And so that is the point on the road we would have to stop at in order to get the minimum distance to the campsite.